Well, very good morning to all of you this morning. I would like to thank you for coming along to this inaugural West Australian Lithium Battery Conference hosted by IDC Technologies. I can see as I look around the room this morning that there are quite a number of experts. And so for myself and for our company, although we're relatively newcomers to this particular space of energy storage, we believe there are many opportunities for innovation and many opportunities to take risks and to do new things. It's an exciting time to be alive. We're looking at new technologies all around us. We can see new initiatives being taken place. I heard yesterday when I was reading through the news that there are things happening down in Kwinana, which I believe somebody will talk to us about later on. There are new opportunities in using lithium technologies in places perhaps we haven't even thought about before. But of course, there are also new risks as we try to bring a new technology into the marketplace. So what I'm going to do first is, because the Note 7 has been such a news-catching sort of an item, I thought I'll show you this little video clip that I found 2 nights ago. It's quite humorous, and well, let's see whether we can get it working.
Welcome back to Source Code, nerds. I'm Emily.
And I'm Philip.
Before you go freak out and get all crazy about where Sam is, don't worry.
He is helping out DC All Access celebrate 1 million subscribers on their live stream, and we all know how much Sam loves live streams.
So let's get into today's news.
Oh, hey, are you watching this on a Samsung phone? And statistically, our Grandmaster Joel Rubin told us that approximately 8,000 to 10,000 of you are. Then you might want to slowly back away from your phone.
Because like a SpaceX rocket, it's about to blow up.
Savage, but possibly accurate. You see that brand new flagship Samsung Galaxy Note 7 phone that was supposed to officially go on sale today, it's actually being immediately recalled because apparently there's a big risk that the phones might explode due to a faulty battery.
Damn. And even though today was supposed to be the official release date, you know whenever a new phone comes out, a bunch of people do everything they can to get it early. Well, that backfires for at least 35 of them.
Literally, because at least 35 of those phones blew up. And my favorite thing about this story is that Samsung is saying it's just a battery cell issue and not a my phone exploded in my pocket and it made a mess of my genitals issue.
I suppose we can all make light of scenarios like this, but for those of us who are in the industry where we try to create new technologies, this is our worst nightmare, isn't it? To come up with a product which you want to release into the world, and just around the time of your competitor's launch, which is iPhone 7, which is due to be launched tonight in the USA, you don't really want to have this sort of bad publicity. So today, we're going to go through some of the things that I've learnt along the Lithium Ferro Phosphate technology path, and as I share them with you, I would like to invite you to sort of go on this journey with me. It's going to be about 60 minutes long. We've trimmed it back from 90 minutes, which is the presentation that I did in Sydney a few months ago. Hopefully you all stay awake. And the important thing is that we would like it to be interactive. So if you've got questions, comments, disagreements, please feel free to raise your hands and we will deal with those as they come up. So here's a bit of a workshop agenda of what we're planning to do. We want to talk about why we actually use rechargeable batteries in the first place, look at different rechargeable battery chemistries. We want to talk about whether lithium batteries are safe or not. What are the different types of chemistries within the lithium brand? And also the different shapes and sizes and types of lithium batteries that are in the market. Are there particular ones that work better? I'll show you a little bit of what we do at Radlink in a couple of case studies. We'll also show you a lot of facts and figures from tests that we have done, tests that have been done at the QA, QC testing phases at our partner's factory in China. And so basically the whole session will last about probably no more than 50 minutes, but I want to, as I say, invite you to participate. So because this is a workshop and not a lecture, we'll try to do some interactive things together, although I know that in an engineering context, technicians and engineers have this aversion to talking to their neighbours, so we're trying to change that a little bit. Okay, just a little bit about myself. I was born in Hong Kong and I've lived in Australia since 1974. I was raised and educated here in Perth. I'm a technology enthusiast and I also have been tagged by many people to be a reverse engineer. You see that little picture of the soldering gun, the Weller soldering gun on the right-hand side of that photograph there? That's where my journey started about 40, 50 years ago. What happened was, when I was living in Hong Kong, my dad was an avid hi-fi audiophile, and he used to buy and acquire all these amazing bits of audio electronics, speakers, amplifiers, preamps, turntables. They all came, truckloads of them all around the house. And although he was a doctor, he loved tinkering with electrical things. And so he brought home one day this soldering gun, similar to the one in that picture there. And he invited me to learn to use it. Well, you can imagine what happened. I started reverse engineering all sorts of things around the house. Anything that could be desoldered were desoldered. And I also made things that probably weren't meant to join together. But anyway, as a result of that, I ended up doing R&D for much of my career, and I love learning new things. My dad, because he was a doctor, wanted me to follow in his footsteps to be a doctor. But unfortunately, because of my strong fear of this red liquid that comes out when you cut yourself, I couldn't really work in a doctor's environment. And so I had to follow my own path. And so I studied at UWA many years ago and graduated with a Bachelor of Engineering degree. And since then, I've been working in an R&D context, creating new products. So for 31 years, I've worked in many awesome companies. And right now I'm working with Australia's largest independent two-way radio integration company, Rattling Communications. And recently, in the last 2 years, we've started delving into the use of lithium technology as energy storage devices, so that instead of using lead-acid solutions. And so as a result of that investigation and research and working with our partners in China, we're now in a position where we can actually offer bespoke lithium battery solutions for the industry. As I say, we're new players in this space, but thankfully the space is large enough for many players to exist. I want to ask this question: why do people want rechargeable batteries in the first place? Well, batteries are required to power all sorts of devices around the house. Your electric toothbrush, your radio, if you still have one of those, your smartphone, and basically the bottom line is you want something which is low cost, that can provide power, that is lightweight and have a long battery life. I can still remember the days when, do you remember the Nokia mobile phones, the really tiny little ones? They used to go for days and days and days on one charge. Well, my iPhone would be lucky to last 36 hours at the moment. So there's this push because of the industry to come up with solutions that will enable us to store energy in a compact form factor and to last a long time. How many engineers are there or technicians are there in this audience do we have today? Can you raise your hands? Yeah, I thought it was a pretty technical audience. Well, can you remember back to about 15, 20 years ago when you had to use nickel metal hydride batteries? Did anyone ever design circuits with NIMH? It used to be a pain to design charging circuitries and all that sort of stuff. And because of poor charger designs, there have been products that have failed very early. I can remember we bought a cordless telephone, the brand of which I will not disclose, which only lasted probably 4 months. I was told by when we took it back for warranty claim, they said, well, these phones are meant to be left on charge all the time. But that was part of the problem. You left them on charge all the time and the battery died. But anyway, there have been, if you use an electric battery-powered shaver or a torch or UPS, many of these products that use the older technologies, older energy storage technologies, they used to fail at the most critical time. And the other thing was, design was very difficult. The sort of circuitries that were available from Maxim or Microchip or any of these people, they just didn't make designing battery solutions easy. But things have changed. Just think back to the last 24 hours of your life. You may choose to talk to your neighbor, or you can just have a think to yourself. Where have you seen a rechargeable battery being used? Just think about all the portable equipment in your life in the last 24 hours, from the time you got out of bed yesterday to now. What chemistry was used? How large were the batteries? Have a chat. We'll give you 30 seconds. Okay, anyone wants to stick up their hand and tell me where they've seen a rechargeable battery being used? Yes. Kids' toys, yes. Yes?
My boat.
In your boat, yes. Big batteries, yeah. Sorry?
In a car?
Yeah, in a car. I mean, you probably drove here this morning and you had to crank up your engine. Yeah, rechargeable battery, lead acid. Anyone else? Yeah, remote controls. I've got one of those here, which doesn't seem to be working. I'm using my fingers. Power tools, yep. Laptop. What about the size and weight of your batteries that you've used? Were they heavy? Were they chunky? Were they pretty lightweight? Any comments there?
Varies a lot depending on the purpose of the device.
Yes, it does indeed. It varies depending on the purpose of the device. Think of the lead acid in your car, probably about 50 kilograms, or think about the one in your boat, which is probably about 200 kilograms. Well, lithium batteries will change a lot of these things. I want to rewind the clock back to the early 1900s to talk a little bit about lead acid batteries. What are the reasons that we still use lead acid battery today? Well, as you can see there are three very good reasons why we still use lead acid batteries. They're readily available. You can even get them from your Big W store if they're going to exist for much longer. They're relatively low cost and they're very tolerant to overcharge. You just stick them on float charge and you just keep them going and going. High surge current, yes, very important as well. But what are some of the downsides of using lead acid technologies? Well, unfortunately, lead is toxic. The batteries themselves are relatively heavy because their energy density is such that they're between 30 to 50 watt hours per kilogram. So to get a 3 kilowatt hour battery will take 200 kilograms. They're also easy to damage and degrade over time. If you apply heat to them or store them in a hot environment, use them in a hot environment, say above 35 degrees C, there's a very good chance that the life of your batteries will significantly degrade. And if you use them excessively discharge them, sometimes they don't recover very well either. Electrodes get damaged and so on. They take a long time to charge, which is one of the big challenges of lead acid, because if you charge them too quickly, they boil literally, and they have a limited cycle life. At the end of life, they can tend to bulge, crack, and leak. All right, I'm sure those of you who have electronic toys will probably be familiar with this, or maybe even in your old electric drills. Lithium cadmium batteries have been around for a while as well, since the 50s. Also readily available, low cost, can be very rapidly charged 1 to 2 hours to full charge, and very high peak discharge current. But also there are some downsides to this particular battery type. For instance, cadmium is toxic. Disposal is a bit of a problem. They've got terrible self-discharge characteristics. If you've ever had one of these batteries and used them, charged them up and wanted to use it 3 months afterwards, the chances that it's lost 40% to 80% of its useful life in that period of time. They also have this thing called memory effect, which I won't go into. It's a chemical effect that causes the battery to lose its capacity if you charge and discharge it at the wrong rate. They can be difficult to charge as well, and they require multi-stage charging systems. The 90s brought the nickel metal hydride batteries along. They were readily available, low cost, good energy to weight ratio, and also have very good, reasonably good peak discharge current. And the most important thing for those of us who had been using nickel cadmium before is that they don't have a memory effect. The low toxicity is also a big plus. But there are also downsides. Self-discharge is something that has come through from the nickel cadmium days. They still self-discharge very, very poorly, and limited cycle life, about 300 to 500 cycles. And because you have to charge them slowly relative to the NiCad, they could be a little bit less useful. Here's a little chart that you will find at Battery University for those of you who are really into doing homework. You will have it in your printed copy as well. Basically, the Battery University has compiled together all the different characteristics of different types of batteries. The four columns that I've highlighted there talk about the batteries that we've already talked about. So really, when it comes to batteries, it's all a case of horses for courses. And for a long time, there was not a huge amount of choice in what sort of batteries you can use. You tended to use your lead acid batteries for your heavy duty products where you need, as we said earlier, a high discharge current like cranking your car starter motor. But for portable equipment, there wasn't a lot of choice. Most people tended to use nickel metal hydride batteries. And this has been the status quo for a long time. The early generation luggable bricks, mobile laptops, all that sort of stuff, they were not truly portable in my opinion. The weight of my little iPhone compared to what my laptop used to be with similar sort of computing power is absolutely astounding. It's all because the batteries have actually become very light. I've suddenly realized that I've been looking at this clock telling me that I've already spoken for 26 minutes. I don't believe it because I suddenly realized that I probably started this clock a bit earlier. So if I've been rushing, I apologize. I'll slow down a little bit. One of the biggest challenges of rechargeable batteries, as I said earlier, is that a lot of them do not deliver power when you need it. For the last 2 years, I've been working with the University of Western Australia with their final year engineering students. And this year, I gave several of the students a challenge. I said, find a way to improve the life cycle of a lead acid battery in a UPS, because I believe it is possible. I gave them a few hints. I'm looking forward to November when they will present their thesis to tell me whether that's possible. Having said that, the only reason why we're doing that is because there's a lot of UPSs out there that may not necessarily be able to take a lithium battery immediately. But the UPSs that fail to deliver power when needed is one of the biggest nightmares for any IT person. I don't know whether you've ever had that before. You know, you're working in an office, the UPS is under your desk, and all of a sudden the lights go out, and you say, oh, great, I've got UPS under the table, and then it starts beeping. Within minutes, 3 minutes probably, and it's supposed to last 30 minutes. And then you rapidly have to shut down everything in preparation for that, the inevitable. In the end, what has happened is that engineers and technicians have started over-engineering solutions to overcome these inherent problems. You started to build systems that are way bigger than you needed to because of this issue. So you find for lead acid systems, some people only would dare discharge their batteries down to 20% depth of discharge, which means your system has to be 5 times the size than it really needs to be, or 50% twice the size. And so electric drills, I can remember picking up an electric drill that's been charged and to go and drill a hole and find that you can get half a hole drilled. So these things are a real problem. But thankfully for us, we're living in an age where we're seeing science and technology moving forward by leaps and bounds. And so it comes down to the question of lithium batteries have arrived on the scene now. Everyone wants to know, are they safe? Now we started with that talking about the Galaxy Note 7. Although it's a joke, it is really not that funny if you think about it, because you really don't want a battery sitting in your pocket or sitting next to your bedside table catching fire when you least expect it. I was reading about this guy who was on a business trip. He brought his Note 7 with him to the hotel. He was charging it with a correct charger. He left it there, and when he picked it up to use it, the thing caught fire. So he panicked and threw the phone onto the bedside table, which then caused a bit of a meltdown in all the equipment around that bedside table. It lit up part of his bed linen as well. So the damage bill from the hotel to him was $1,800 for that little incident. Samsung have just told, it was in the news yesterday, Samsung have offered to pay that $1,800 bill to the hotel because of the fire. So lithium batteries are safe. There is a yes or no sort of an answer. You probably have seen the earlier generation LiPo, the lithium polymer batteries. This is one taken from an iPhone 3. They used to swell up after about 1 or 1.5 years of usage and start to get into the electronics and create damage. Poor Tesla had a few problems as well. This is a picture taken in the UK. Remember back in 2008, there was a lawsuit between Apple and Sony about the batteries, the lithium batteries that were inside their MacBooks. They caught fire, and quite spectacularly as well. And then, of course, in the last 2 years, the hoverboard market You remember Russell Crowe and all those people who tried to bring hoverboards onto aircraft for their children and so on? Well, they were quite a risk. And of course, a lot of these risks could have been avoided if the designs had been better. The question is, under what conditions are lithium batteries considered unsafe? Well, the earlier generations of lithium-ion batteries were quite difficult to charge. I don't know whether anyone's ever tried to build electronics in the early days before the chipsets came out, trying to build the right constant current charging modes and constant voltage to stop them from overcharging and so on. And also some of the earlier chemistries had a bit of a heat problem. When you charged them rapidly, they built up a lot of heat. And with the thermal runaway temperature around the 130-degree mark, it didn't take a lot to actually push your battery into the danger zone and cause them to catch fire. And of course, if you were discharging the batteries, that's the same problem, because when you discharge a battery, the heat in your cabling, the heat in the chemical reactions themselves in the cells, that also could lead to fires. If you were to shock, impact, compress, or pierce one of these lithium batteries, because you're shorting through different layers of the anodes and cathodes, you would also see fires. Because you're dealing with something that's got a very high energy and power density compared to the good old lead-acid battery, we're talking about 5 times to 8 times for the same amount of weight. These batteries, when they had thermal runaway, they really had thermal runaway problems. But of course, as we've discovered, these problems haven't gone away in the most recent iteration of the Samsung battery. So what happened to this particular Samsung Note 7? Well, according to the owner, I listened to his YouTube video. The links are there. They will be provided to you from IDC later when you get an electronic copy of my presentation. If you listen to what the owner claims on the video, he said he was using the official Samsung charger. The fire only started right after charging ended. My gut feeling is that the battery probably expanded. Some of the internal contacts probably welded together, and as a result, shorted out maybe one or more of the cells in that battery pack. That then caused thermal runaway and fire. The ABC News reported last night, based on our investigation, we have learned that there was an issue within the battery cell. An overheating of the battery cell occurred when the anode to cathode came into contact, which is a very rare manufacturing process error. Well, as you know, for those of you who use batteries, the anode is the positive terminal and the cathode is the negative. They're not really meant to touch each other very often. But when they do, they can create a bit of a problem. Here is a video that I was going to show you, but I couldn't get it downloaded, so I'll show it to you in a series of shots. This is a laptop battery that had a thermal runaway problem. The owner specifically wanted to show how dangerous it was to use lithium polymer batteries, lithium cobalt batteries in laptops. What he did was he stuck a heater, an electric heater behind it. You can't see it in this particular picture, but at T equals 0, the battery was running fine. At 12 minutes in, the battery was still running okay. The heater was on. And at 18 minutes, the first cell ruptured because of it having reached the 120-degree C trip point, the thermal runaway point. And 27 minutes in, 36, 44, I think it's actually seconds, I apologize, 44 seconds. 1 minute and 6 seconds, he started pouring water onto it. It's to cool it down. That's why I said earlier, if your phone gets too hot, put it into the water. In fact, there was a story that I read about a guy who had an Apple iPad that was overheating on a plane, and the stewardess said to him, basically, sir, can you just put it into this tray? And so he put it into the tray, and she immediately poured a bucket of water into the tray just to cool it down. That's the correct procedure for cooling down overheating batteries, apparently, on a plane. So there you go. The bottom line, really, when it comes to lithium batteries is stick to the design guidelines, because that's the only way you'll stay safe. And the trouble is, if the design guidelines are not clear, is that you have to use your common sense as well. Let's look at some of the chemistries that are available today in the lithium battery space. Lithium cobalt oxide is a very common battery used in a lot of electronic equipment, especially in smartphones, laptops and cameras. The reason is that they're lightweight, but they have got a lot of energy storage capacity. They're nominally 3.6 volts, but they can be charged relatively quickly in 1 hour. You would have seen some of these in your earlier generation sort of laptops and cameras. They could be charged very quickly. And they had a reasonably good life cycle, 500 to 1,000 cycles. But the problem is the thermal runaway temperature, 150 degrees C, due to overcurrent. And there's a toxicity issue with cobalt. Makes them a little bit unsuitable. Lithium manganese oxide is another chemistry that's been around for a while. This runs at 3.7 volts, and we find these in power tools, medical devices, and electric cars. They've got a limited life cycle, 300 to 700 cycles. Amazing thing about these is that you can discharge them at 10 C. So if you've got a 2 amp hour cell, you can get 20 amps out of it, which is pretty amazing. But you must not over discharge them, just like a lot of all these batteries. Thermal runaway temperature is 250 degrees C. Lithium nickel manganese cobalt oxide, NMC, is also a 3.7 volt chemistry. High energy capacity, can be charged at 1 C and discharged at 2 C. So it suits a lot of e-bike, electric car type applications. When you need 1,000 to 2,000 cycles, which is probably about 3 to 6 years sort of life, they're quite suitable. Thermal runaway doesn't take place to 210 degrees C, so it's relatively safe. My favorite, lithium iron phosphate or lithium ferro phosphate, or just LFP. The nominal voltage for these cells is 3.2 volts. I've got a few here on the table, on the podium here. This is a 18650 cell that we use, as well as a 26650. These are all 3.2 volts. So this is 5 watt hours, 10 watt hours, and 15 watt hours of storage. They've got reasonable energy storage capacity. You can charge them relatively quickly, but you can also discharge them relatively quickly as well. From our perspective at Rattling Communications, the most important aspect of this battery's upside is that it can survive high temperatures. It has, depending on the manufacturer that you choose, they can last between 1,000 to 6,000 charge-discharge cycles. And that is dependent on the depth of discharge. If you use your battery down to the last millicoulomb, drain every drop out of it, then the cycle life will be shortened. But the useful thing is that they can be used for high load currents as well. And with a trigger point in the thermal runaway curve at 270 degrees C, there's a relatively low risk of thermal runaway for most of the applications. We can overcharge them generally without too much damage, and so it has been known in the industry, and many people have called them the safe lithium, and it's good for Australian conditions. I'll explain further. This graph here shows you the different chemistries that I've already mentioned. As you can see, the lithium cobalt and the lithium nickel manganese cobalt have got incredibly high energy storage capabilities. The LFP is not so good, and then further down you've got the nickel metal hydrides, nickel cadmium, and lead acid. So as you can see, if you need lightweight, high energy storage, lithium has really got to be the way to go. The question really comes down to what can you afford to use and what sort of safety safeguards you need to create. This little picture here is very helpful if you're trying to get an angle of the size, shape, and weight of these things. We've chosen a case of a typical sort of a lead acid battery, 12 volt, 22 amp hours, so that's 260 watt hours of energy. The weight of this lead acid battery here is 7 kilos, occupies a volume of 2.3 litres. The lithium ferro phosphate is about 1/3 of the weight at 2.6 kilograms and uses about, just over half of the volume of the predecessor. The lithium cobalt oxide, which is the one that you see in your laptops and all your high energy requirements, is even lighter again, 1.65 kilos. Compared to 7, you can fit quite a lot of that and you will get basically 5 times, as I said, the energy density. Also, the volume that it occupies is significantly smaller, as you can see. This table is the same table that I showed earlier, but this time I've uncovered all of the details, and you should be able to read that, I think, in your printed copy. But if not, you can follow the link that I've given you. All right, this is an interactive session again. I want to just make sure that you're still awake. I know I can see most of you are still awake, so that's good. But I'm going to ask 5 questions, give you 1 minute just to think back through what you've read. You can look through your notes if you need to, just to make sure that, you know, we can all remember some of these key facts and figures. We're about 50% into my talk, so we're on schedule. Before lithium batteries came along, what rechargeable battery chemistries were available to a design engineer or product developer? Question 2. List 2 reasons why lead-acid batteries are still a viable option for some energy storage systems. Question 3. Name at least 1 reason nickel metal hydride batteries have fallen out of favour for use in portable equipment. Question 4. Of the lithium battery chemistries discussed so far, which one has the highest energy density? And finally, what are some of the key benefits of using lithium ferro phosphate or LFP batteries? You've got 1 minute. Okay, let's go back to question 1. Before lithium batteries came along, what rechargeable battery chemistries were available to a design engineer or product developer? Any brave souls out there?
Nickel cadmium.
Nickel cadmium, yes. Lead acid, yep. Nickel metal hydride, yep. Okay, so you were listening. Question 2. List 2 reasons why lead acid batteries are still a viable option for some energy storage systems.
Rugged and reliable.
Sorry?
Rugged and reliable.
Rugged and reliable, yes.
Charge.
Easy to charge.
Cheap.
Cheap.
High crank. High crank.
Sorry.
High current draw.
High current draw, yes. Well, you've actually got more ticks than I have there on the screen. That's good, that's good. I was a bit biased, you see.
Quite safe as well.
Yeah, they're relatively safe, except for when they explode. Talk to some of the people who have had experiences where the gas build-up in the chamber above the electrode, above the cells have been filled with hydrogen, and then on the first use, the little spark that happens ignites the whole thing and blows the whole thing apart. So it's not very good at that level. But typically, if it's in a vented environment, it's good. Name at least 1 reason nickel metal hydride batteries have fallen out of favour for use in portable equipment. I'll get some people from this side. They're very quiet on this side. Self-discharge, yes. Must be managers on that side. I'll put the question. I'll put the answer. Sorry. Life cycles, yes. And of course, the charging time can be a bit of a pain if you want something charged quickly. They do get quite warm as well if you want to push them to the edge. Question 4. Of the lithium battery chemistries that I've mentioned so far, which one has the highest energy density?
Lithium ion cobalt.
Sorry.
Lithium ion cobalt oxide.
Lithium cobalt oxide, yes. Not lithium ion, yes. Cobalt oxide, yes, correct, yes. Yep. There are actually 2. It's a trick question. NMC is very similar. They've got a very high energy density as well. And I think it comes down to costs, because the LCO technology is a little bit cheaper. NMC is expensive, so people generally use the LCO in preference, but both have very good energy storage. And the amazing thing, of course, is how much you can jam into the equivalent size of a lead-acid battery. It's just stunning. What are some of the key benefits of using LFP batteries? Safety. Yeah. Well, I've put them up there just to remind ourselves. They can achieve very good cycle life if we look after them. Later on, one of my last slides, so this will keep you awake. It's not in your book because it's a very new slide. It's just been introduced last night because I've been doing the mathematical modeling of the life cycle of an LFP against depth of discharge using a whole bunch of data that's come in. And it's quite exciting. On a graph, when you can see it, it actually makes you realize why it's such a good battery to use. The important thing for us in Australia is that these are good batteries for use in a high temperature environment. If you were to put a lead acid type solution into the outback, maybe in a hut that's not air conditioned, then the chances that your lead acid battery will need to be replaced every 18 to 24 months. Lithium ferro phosphate, on the other hand, without air conditioning, will do a lot better. The other thing is zero maintenance. Some of the lead acid batteries, although they say they are low maintenance, they're not truly low maintenance. You still need to inspect them. Lithium ferro phosphate batteries that we're currently working on in our own labs and so on, they will eventually have what we call a smart BMS, which will allow us to get the batteries to talk to each other, much like an Internet of Things scenario, so that all the batteries can talk back to the control system. I'm sure this is already happening in other parts of the world, and we're catching up, but we're trying to introduce it into the environment that we're playing in, which is in the communications game. I showed you some of the battery cells just now. The 18650 cell is one of the types of cylindrical lithium battery cells, lithium ferro phosphate or cobalt oxide or NMC cells that you can get. The reason for the numbering is that the 18 stands for the diameter, 18 millimeters in diameter, 65 millimeters in length. And the one on the screen there is an LCO, lithium cobalt oxide, 3.6 volts, 2.2 amp hours. The next one down is the 26650, so it's 26 millimeters in diameter, 65 millimeters long. And the one below that is the large cased one, 32 millimeters in diameter, 65 millimeters long. When we use these in the LFP form factor, we can get 15 watt hours per cell out of these, so they're quite high energy density. There are other types of batteries, and I'm sure you already have seen these before in your travels, and you may even be using them. The prismatic cells are very common for people who need to get very high, compact storage of energy. Because of the rectangular prismatic structure, you can jam a lot of them in together. There are certain downsides, which we'll talk about shortly. Another type of batteries, which is what you find inside your phones or your tablets, is a pouch cell. So they're very thin. The challenge there is that they can also be easily damaged. Okay, so which cell would work best in your scenario? Let's go through some of these. Prismatic cells, you've got 3 ticks there on the top 3 things. They're encased in an aluminium or steel case for stability. So in other words, the risk of you damaging them is relatively low. They're jelly rolled or stacked in their design to give you the energy, give you the density that you require. So therefore the cells are very space efficient. However, they used to be a bit costlier to manufacture, and you find them in use in electric powertrains, in electric cars, electric bikes, all that sort of stuff, in energy storage systems. The next type is the pouch cell. They're some of the newer technologies that we see. When I was in Las Vegas a couple of years ago to look at the Consumer Electronics Show, there were lots of people bringing out new types of pouch cells with all sorts of shapes and sizes. They provide a very lightweight and cost-effective solution. The challenge is to keep humidity out of these because humidity apparently shortens their life, and high temperature also shortens their life. There's a swelling of up to 10% after 500 cycles, after about 1 and a bit year of use. And as I showed you in an earlier photograph, the iPhones suffered from that problem. They actually swelled up into a bit of a bubble. It serves very similar sort of applications to the prismatic cell, but most importantly, it's used in a lot of portable equipment. The cylindrical cells, which I've shown you, they've got good high specific energy, good mechanical stability. Because they're cylinders, they're actually harder to damage. They're easier to automate in the manufacturing process. If anyone is interested, I've got a video of how these things are made. They cycle well in terms of usage. They offer a good long calendar life and relatively low cost. Challenge here is that they are rather hard to compress into a tight space. They don't have the ideal packaging density. However, having said that, we've got some batteries at the back there that Nick can show you afterwards, where we've managed to squeeze 1, 2, and 3 kilowatt hours into 19-inch rack-mounted cases. So really, depending on your specific requirements, you need to weigh up what are your pros and cons and select a particular lithium battery form factor for your use. I just wanted to put a little bit of a commercial about ourselves at Radlink and what we do. We sell off-the-shelf lithium ferro phosphate products. Now you can see some of that, as I say, on the table at the back there. They come in a form of lead acid cases, so they go into standard form factor, but they're higher energy storage, and we've also added some additional electronics onto them to help you diagnose problems. We've got a little battery level gauge that's built in, so you can actually see how your cells are going and so on. But in addition to selling these off-the-shelf solutions, we also sell bespoke solutions, and because of that we have to be very selective about what we sell to our customers. And our customers range from mining, telecommunications, utilities, healthcare, and so on. Some of you here are possibly even clients of Radlink today. And because we have to build mission-critical systems, we're particularly cautious about the designs that we undertake to make sure that you won't come back to us in 2 years and say, well, this is not working. So we always ask ourselves the question, is it fit for purpose? Is the particular form factor correct? There's a battery, again, at the back there, which has a metal handle on it to make it easier for you to carry it around. It's got a high rapid fitment solution because it comes with a connector rather than having two lead terminals or screw terminals. Because we're not white box shifters, we try very hard to design solutions that are fit for purpose. This picture here shows some of the things that we manufacture ourselves. These are skid-mounted energy storage systems with built-in telecommunications equipment. On the top right-hand side there, you see the solar panels, which harvest the energy from the sun. They then go into the energy storage system. Now, this particular one in this photograph still uses the older lead-acid solutions. And then there's energy management system to look after how much charge or discharge you need to allow to enable the batteries to operate efficiently. Then there's energy distribution to different other equipment. And of course, energy conversion is very important. You're taking the energy in from the sun. It could be up to several hundred volts DC. It's rectified and stepped down to the appropriate voltage, often around 48 volts. But you need to convert it back to other voltages, maybe 240 volt AC or similar. So it's really a whole ecosystem that we need to think about rather than just batteries on their own. And so Radlink, we do this sort of stuff. We don't just make batteries, we do the whole ecosystem. And of course, part of the ecosystem is that we are into integrating communication systems, whether it be a Tetra radio node or a DMR radio node or Wi-Fi, WiMAX, you name it. So these things have a purpose. They provide energy for things sitting in the middle of nowhere. And as you can see, they will have to withstand very high temperatures. Those enclosures are not air conditioned. So they're basically just passively cooled. Sometimes they've got fans to assist, but there's no air conditioning. So for the designs that I've done so far for Radlink over the last little while, over the last 10, 12 months or so, they've all been based on the 26650 cell, this particular cell here. It's got an energy capacity of 10 watt hours, so if you series and parallel them together, you can get really good products out of them. You can see some of the features there of where we're at. Just a few case studies, again, they're in your notes. This is the battery that I mentioned. We converted a 23 kilogram lead acid battery into a 7.5 kilogram LFP-based battery with a rapid fitting connector. We've done a job for the Water Corp as an experiment to reduce the size to take out some batteries that were due for replacement and replace them with 3 50 amp hour batteries in parallel. Elizabeth, who will be speaking later today, she'll talk to you more about this particular product. These are our 19-inch rack-mounted batteries that you can see one off down the back. They're basically designed to be high energy output, modular scalable, relatively lightweight compared to lead acid, hot swappable, and it comes in a standard form factor, 19-inch form factor. That's what they will look like in a 19-inch rack in conjunction with all the other equipment around it. Now, for those of you who love statistics and facts and figures, many of these are already in your notes, so I will jump through them pretty quickly, but there will be a few extra slides that I've added in the last 48 hours based on tests that I've just completed. The cells that we talked about, these are the characteristics of the cells, 3.2 volts, 3.2 amp hours. They can be discharged at up to 9.6, so that means 3C. You can discharge them in 20 minutes. Or if you're really pushing them, you can discharge them at 15 amps for 5 seconds. So they do have the ability to deliver peak power, but not recommended. They're relatively light at 86 grams each. This is a curve. The blue curve shows the charging characteristic of that cell. Basically, it rises from 2.x volts all the way up to the termination voltage of 3.65 volts. So these cells have to be charged with constant current initially, and then constant voltage. Constant current can be up to 1C. In this particular case, it's half C, so it's 1.6 amps. And then when it reaches its termination voltage of 3.65 volts, the cell virtually draws nothing. 32 milliamps is what we're talking about, sort of 1% of the original starting current. Similarly, when you discharge, that's the pink curve, you can see it has a very, very flat discharge characteristic. The following slides are all taken from real QA/QC data taken from the factory. This particular one shows the discharge curves for different discharge currents, starting from 0.1C, so that's a 10-hour discharge, to 3C, which is discharge in 20 minutes. You can see that despite the fact that we're discharging a lot of current, the voltage stays extremely flat over most of its useful life. By comparison, if we were to look at a lead-acid battery that we have replaced, the lead-acid battery claims to be 28 amp hours, but that's only if you discharge it over 20 hours. If you were to discharge it in 1 hour, it loses about a quarter of its capacity, down to 21 amp hours. With the LFPs, that is not the case. This is a curve taken from the first batch of 3 kilowatt hour batteries that we took delivery of from China. And as you can see, it's a beautiful solid red line at around the 50 volt mark. And that's discharging at 57.6 amps. That's a fairly high amount of current out of one of these batteries that we're doing. And it reached its capacity of 3 kilowatt hour just shy of 1 hour. These are different characteristics at different temperatures. The LFPs don't work well in the lower temperatures. Anything sort of left of the cyan colored line, it doesn't perform well. But when you're up in the higher temperatures, it certainly does perform well. We recently built our own temperature test chamber for testing our batteries. We basically put our batteries inside and turned on a heater just to raise the temperature of the equipment up to 55 degrees C, just to make sure that we can deliver what we promise our customers, that they will work to 55 degrees C, and they do. This is a charge curve. The test started at 20 degrees C, and because I haven't got the ability to animate this, you just have to focus on the picture and look at that orange colored line. The orange colored dotted line shows the capacity of that cell, and the gray line is the voltage. Notice at 20 degrees C, we're getting over 3,100 watt hours out of our battery pack. You elevate the temperature to 25 degrees C, and it goes up to 3,133. Go up to 55, and it goes up even further. So unlike some other battery chemistries where if you push the temperature, you actually damage the cells, we find that these batteries will work quite well at high temperatures. But not all lithium ferro phosphate batteries are made the same way. The particular factory that we have chosen to work with in China supplies their batteries into the military and into medical applications. So we know that these are high-grade cells. I recently asked them to supply me with cells, what we call grade B cells, for use in domestic type environment. They said, go away, we don't want to talk to you because we don't sell grade B cells. And in any case, if they are grade B cells, we would trash them anyway. So that was very encouraging to me to know that our supplier doesn't want to sell grade B cells. So they only want to sell these top grade cells. This particular graph here shows the self-discharge characteristics at 25 degrees C. Over 12 months, basically the cell has retained 87% of its original capacity. Lead acid batteries, unfortunately, don't have quite the same characteristics. Where the arrow is pointing is the same discharge point, or 86%, and if you're looking at that, it's only about 3, 4, 5 months worth of use before of self-discharge before you get there. This is a graph showing the decrease in cell capacity after continuous charge-discharge cycles at 1C. So you charge the cell at 3.2 amps, discharge it, charge, discharge. Basically, every hour you go through it just short of 12 times a day. And as you can see, at 2,000 cycles, it's still up in the 90% sort of region of the original capacity of the cell. This graph is a little bit confusing. Basically, what people ask us is, if we were to reduce the depth of discharge on a system, how much more life can we get out of our battery pack? The answer is that if you discharge them lightly, they live a long time. In fact, if you just float charge them, they will almost live forever. If your metal case doesn't corrode and your cables don't get eaten by the cockroaches and everything else. But basically, that graph is a bit hard to interpret, so I've created a new one. I'll just, this is a comparative graph for lead acid battery. If you were to discharge a lead acid battery at 100% depth of discharge, it becomes pretty useless after a very small number of cycles. I think this is the curve that probably would be most useful. It's not in your document. The orange line, the heavy orange dotted line, shows the upper limit of the life of a lithium ferro phosphate battery, and the light, or the smaller dots, reveal the lower limits. What it shows is that to interpret that graph, what you're saying is you want the line to be as high vertically as possible, because on the left you can see that the axis is typical lifespan in years for daily cycling. What it shows is that if you are to cycle your battery at very high depths of discharge, which is on the bottom on the X scale, you still achieve way better performance than your lead acid. All of the data here has been synthesized from a lot of manufacturers' data that I've pulled together and mathematically modeled it to help me to select a right solution for you. So if you come up to me and you say, I've got a 100 amp load, I need to discharge for 48 hours, what sort of batteries should I use? I can actually tell you. If you were to go for this one, it will live this long. If you go for this slightly more expensive one, it will live that much longer. So this is what all these curves are for. It's just for selection processes. At the moment, in the industry, there's no standard way of selecting batteries, and we're trying to improve that. I'm running out of time, so I won't do this design example. It's in your notes. Basically, we wanted to design a 36 volt, 90 amp hour scooter battery, and I show you the steps that you will go through to actually get there. The other thing about lithium ferro phosphate batteries is they do not emit a lot of heat. This is a tool or toy that I bought from the Apple shop. It's well worth having for those of you who've got iPhones. It's a FLIR camera that plugs into the bottom of your iPhone. And it also, you can actually get it for your Android as well now. All of these pictures were taken with that. So when I'm in China and I need to check on the performance of the tests, I can actually check. Because the Chinese, unfortunately, they use a very clunky FLIR camera. It's almost the size, you know, those old, in the movies, you've seen these old cameras on a tripod with like a wooden box. Well, theirs is a bit like that, and it's very unportable. So if you're trying to move it around to take pictures, this thing can take you places very, very quickly. So what you see here is the losses in your battery pack often do not come from the cells. They actually come from your cabling. You can see the battery management system, which is there. That's hot. The circuit breaker, that's hot. But the cells themselves, they're actually running relatively cool. Typically what we find is that running at 1C, if you're discharging the batteries over a 1 hour period, If your ambient temperature is 40 degrees, the cells will go up to about 50 degrees. A very, very small rise in temperature. So it's relatively safe for all the stuff that you do. So in addition to that, we use battery management systems to protect against misuse and abuse. You need to protect the batteries against overcharging, so you need to clip it when it's over voltage or under voltage when it's over discharged, over current, short circuit, over temperature, and of course you need to balance the cells as well. So whenever there's a fault condition, you need to be able to stop the battery from operating. So to wrap up, lithium batteries have been around for a fairly long time, but the rate of adoption only took off with smartphones having become a commodity. EVs, electric vehicles, and solar PV, solar photovoltaic systems, are now driving new requirements and opportunities.